Welcome back to the study of sequences, recursions and difference equations. So here I focus on the name difference equations, but we have seen the other words as well. And in this sequence of videos, we will look at the qualitative behavior of these recursive relations or difference equations. In particular, we are interested in the dynamics, which means steady states, points which do not change, things which oscillate around, etc., etc. Now, to remind you, we had a various number of notations for the same thing. So we called it sometimes an plus 1 is equal to f of an, or we used explicitly a t to indicate time. So then we have xt plus 1 is f of xt. Or if we particularly talk about populations, we often use n for like a population number. So then n at t plus 1 is f of nt. So the population number as the next time step is derived from the previous time step nt by this so-called updating function, and the updating function is f. For such a difference equation, we define an equilibrium or a fixed point to be a state which doesn't change. So then if I go from xt to xt plus 1, I do not change, I want to keep the same, which means I satisfy this equation, x hat is equal to f of x hat, and then this value is called an equilibrium or a fixed point. X hat is unchanged by f. So let's look at two examples. The first one is the linear population growth model, which we have seen earlier. So let's say at one day we have a bacterial population at nt, which each day doubles. So that's why the 2 is here. So then the next day we get the double amount. So let's say initially we have 2, then we get 4. Next day we have 4, and then we get 8, etc., etc. So let's look at equilibria of this equation. So let's try to identify all the terms. So the updating function f of n is the right-hand side, so that we 2n. And then equilibria n hat satisfy the equation n hat equals f of n hat. So let's write this out. Then we have n hat equals 2n hat. So we can move one n on the other side, and then we get 0 equals n hat. So there we go. We get one equilibrium at n hat is equal to 0. Very simple. Now, of course, there might be more equilibria, and so I'll show you another example where this happens, which is the logistic map. So again, let's identify the terms. So the updating function in this case is 2x 1 minus x. So it's really easy, right? You just remove the index t from this bit here, and this is your updating function. And we need to satisfy the equation x hat is 2x hat 1 minus x hat. So now we have something to solve. So maybe multiply out the right-hand side. Then we have 2x hat minus 2x hat squared. Move everything to the right side, so then we get 0 is x hat minus 2x hat square. Then I can factor out a common factor x hat. So x hat 1 minus 2x hat. And this has to be 0, and so I have two choices. The first factor can be 0, or the second factor can be 0. So this implies that either x hat is 0 or x hat is equal to, so the bracket is 0 for x hat to be 1/2, so 1/2. Which means we find two equilibria. There's a really cool relation of the equilibria to intersection of two curves. So let's try if we can figure this out. So first of all, we have an equation y equals f of x, which is the equation for the updating function. And then secondly, we have this equation for the fixed point, which is x equals f of x. Now I removed the hat, but it's the same equation. But now if I have the green and the blue equation, this implies this here, that y equals x. Right? You just equilibrate these two equations, so you get y equals x. But now y equals x is a diagonal. It's a diagonal line, this one. So the line y equals x is a diagonal line, and y equals f of x is the updating function, and all these equations are satisfied, so it's the intersection. It's the intersection of the updating function and the diagonal line. So that's what I wrote here. Equilibria lie on the intersection of the updating function and the diagonal. So let's look at the logistic map again. Here I plotted the whole thing. So this is the logistic map. This is actually the updating function. F of x is 2x, 1 minus x. The red line is the diagonal. And the intersection points are very clear. So we have an intersection point at 0, and then we have an intersection point here, which is exactly at 1/2, which were the two fixed points which we computed earlier. So you can see it very nicely in a graph like this, where you just plot f and the diagonal and the intersections, and you are done. So let's do that for the linear growth model as well. So here's a linear growth model. Now I use a general term for R, and I look at several cases for R. So we began with R is 2, that's the example we did before, and you see the only intersection point is here at 0. So the only fixed point R hat is equal to 0. Now let's look at the other case, R is 0.5. Then the curve is below the diagonal, and again the only intersection point is here, so R hat is also 0. So what happens if R is 1? Let's write down the difference equation. So n at t plus 1 is equal to nt. So there's no change. There is no change. So which means every n hat in the real numbers satisfies n hat, equals n hat, obviously. So which means every n hat is a fixed point. So each n hat is an equilibrium. And of course, if you look at the graph, they overlap. So each point here, everybody would be an equilibrium. Cool. So we can have 1, we can have 2, as we've seen earlier. We can have many, we can have even a continuum of these. Let's study this again for the logistic map, but this time for a general parameter c. So I would like to find the equilibria for a general parameter c now. So the equation I need to solve is x hat equals cx hat 1 minus x hat. Multiply this out, so we get cx hat minus cx hat squared. Bringing the 1x hat to the other side of the equation, then we get c minus 1 times x hat minus cx hat square. Again, multiplying out a common factor of x hat, so that we get x hat c minus 1 minus cx hat. We get a product of two factors which has to be 0, implying that either the first one is 0 or the second one is 0. Now I write this as c minus 1 minus cx hat is 0. So this is equivalent in saying that x hat is 0, no change here. But this I would like to simplify a bit, so I get c minus 1 equals cx hat, which then implies x hat is equal to c minus 1 over c, and then the standard way to write this is actually 1 minus 1 divided by c. So we get one fixed point all the time, which is 0, and then we get a second fixed point depending on the parameter of c. And now in these graphs I've shown this to you. So if c is 0.8, then actually this term 1 minus 1 over 0.8 is less than 0. So it is not seen if I only show the positive part of the curve. So here we have the 0 fixed point. If c is 2.5, then we get a fixed point here and a fixed point here. If c is 3.8, then we get a fixed point here and a fixed point here. And then this fixed point here has a location 1 minus 1 over c, and same here, this is 1 minus 1 over c. So that's really cool, isn't it? You just need to look at these intersections. The next thing is we like to talk about stability. So stability means that if I start very close to a point, then I converge to that point. So we call it asymptotically stable if a solution starts close to an equilibrium point and converges to that point. And it's called unstable if solutions go away.
This is easily explained on the population growth model,
which I write down here again. Nt plus 1 is Rnt, where R is a growth parameter. And I would like to look at the two cases where R is bigger than 1 or where R is less than 1. So let's look at an example for R is bigger than 1, so maybe R is equal to 2. And then let me start with a population, let's say, of 1. So let's say initially we have one cell, and then the cell divides and we get 2 cells. So then N1 would be equal to 2, and then N2 multiplies again by the factor 2, so it doubles again. So then N2 is 4, and N3 is 8, N4 is 16, etc., etc. Okay? As you can clearly see that this does not converge to 0, or it does not converge to any other number, in fact. This really goes to infinity, so here we would say the equilibrium 0 is unstable. Now let's look at the case R is less than 1, so for example 1/2. If R is 1/2, and again I start with 1, then in the next step N1 would be 1/2 of it. And then N2 would be 1/4, and N3 is 1/8, etc., etc. And so then this clearly goes to 0 as n goes to infinity, right? So in this case, n hat is equal to 0 is asymptotically stable, and sometimes we don't say asymptotically, we would just say it is stable. So let's summarize. First of all, we looked at difference equations of the form xt plus 1 is equal to f of xt, where we play around with the updating function f. And we saw that equilibria or fixed point arise as intersection points of the updating function and the diagonal. So what we have to do in the future is we just plot the updating function, which can be more complicated than we had it so far, and then we plot the diagonal line, bzzzt, and then we can just read the fixed points, right? So then the fixed points would be here and here and here and here and here. So very simple. We talked about stability. So if solutions near an equilibrium converge to the equilibrium, we call it asymptotically stable. If solutions move away, we call it unstable. Stable. Yep. Stable. Yeah, quite stable. Yep, stable. We are in perfect equilibrium. Perfect equilibrium.